and we are recording. So it's been a while.
Hello, hello, future people.
Yeah, so I believe the last recording that it's public on YouTube is like the 20. Actually, not even. Maybe the private one is also the May 23rd. So it's almost a month. It's been passed since we recorded that last time.
Yeah,
So
stuff happened.
yeah, stuff happened and we had to postpone many times, mostly because of me. But now we are here, right? Now we are here. And we're gonna start. We're gonna try chapter 8 and chapter 9 today. Chapter 8 is basically an extension of chapter 7. After we understand functors, we understand its family because it's a family of it's a very
Things.
cohesive and like makes sense family in that sense.
Yeah, the family is a very natural extension of the base concept. You will see that in category theory, everything is very natural.
And then you see chapter 10, natural transformations.
Yeah.
Okay. Okay. So let's go. Bifunctors. So the intuition behind this one is kind of like, what if you want to map two things at a time, right? So I had this exact problem once when I wanted to fmap in either, but I wanted to fmap the two things instead of only one thing. Uh, so that's basically the intuition. What if you have a tuple and you want to fmap, we want to pass two functions and fmap the two members of the tuple, right?
It doesn't
Uh,
have to be a tuple, can be a sum type,
it can
like
be a
in
sum
your
type.
leader
It can be
example.
a sum type. So basically, we're gonna do a Cartesian product, right? So we're gonna try to discover if there is a map between the Cartesian product of the category C and D to the category E. Um, so this is kind of what we are looking for here. So we have uh, what is this? The composition of tuples is the tuple of the compositions. I guess that's how you say that.
Essentially.
Um, oh, this is actually to identify if bifunctors are indeed a category, right? And the answer is yes, because if this is the identity and it is associative because it's using composition, and it has a composition operation, so that means that it's fine. And this is just for simplification, right? This is just a tuple just to make an example. Not necessarily
I
needs to
mean,
be one.
technically, if you think about it, a bifunctor, it kind of is a pair of functions, right? Because you need to be able to transform both components.
No, sure, but this could be something else aside from being a tuple necessarily. It could be another product type.
Well, yes, I
Cool,
suppose it could.
good. So here's the Haskell's type class that defines bifunctor. So it has a very how will you say this, trio. So we have a bimap, which is the one that I used when I searched for how can I map the two things of an either, or how can I map the two things of a tuple, of a pair, sorry. You pass the two functions and you pass a bifunctor, and you're gonna get the bifunctor with applied to the two functions. And you have some auxiliary operations. What if you just want to apply an operation to only one of them? So that's what this does. So you have the first and the second. And again,
Amazing.
if you orient yourself using the types, you're gonna see that there's an A here and the same A here, and there's a B here and the same B here. So that's a little bit of intuition right there.
Yep.
Uh, this is the drawing of the bimap operation,
A very nice picture.
uh, and these are the ones like separately. So you have the first and the second as well. Um, and this is pretty much the idea, right? So of course we are kind of jumping over some of the like this is kind of important to know that instead of having to check we have having to translate functional laws to bifunctor stuff from functors to bifunctors, it's enough to check separately each of them, which is kind of useful. If you have a mapping from a if you have a mapping from a pair of categories to a third, and you prove that it is functorial in which argument separately, then the mapping is automatically a bifunctor. So that's very useful. That's very useful. Okay. Then we go to product and co-product bifunctor. So now we're going to go to some examples of even implementation. So here we have the tuple example, which is kind of obvious, right? Like it
It's
says, it
natural,
writes
you could say.
itself. It writes itself.
You could even say it's natural.
So you have a thing, and you have another thing, and you happen to have a pair of functions here that transforms each one of those things to the other things that you want. So you just do that. That's how we roll. So here
Very straightforward.
we have an example of using a tuple as a function, very useful to know as well if you didn't know. And then we have the example of this is an example of a product, and this is an example of a co-product, which is a sum type. Um, then it makes a comment about the monoidal category, right? I mentioned that set is a monoidal category with respect to Cartesian product with the singleton set as a unit, and it's also a monoidal category with respect to disjoint union with the empty set as a unit. So I think we have seen this before in chapter 5 or 6 or whatever.
We're gonna
Uh,
see this again very soon, actually, right?
and what I have mentioned is that one of the requirements for a monoidal category is that the binary operator be a bifunctor, which is kind of weird. What is the monoidal category binary operator? Is that mappend?
No, it would be the binary operator. In this case, it would be either the tuple constructor or the either constructor, like the type constructors actually, not the actual data constructors.
Mm. Okay, so I don't have complete intuition about this because I have to remind myself what's up with the monoidal category. But we're gonna see this very soon again, according to you and according to the book itself, because we're gonna have to see naturality at some point. Functional
Functorial.
functorial algebraic data types. Um, so now we're gonna talk a little bit of about some other examples. So in this case, it's gonna be the list and the maybe, right? We're gonna be introduced to parametric polymorphism, I believe. Um, where we use ADTs, algebraic data types, to make products and coproducts. That makes sense. Um, what we want is to know that if an ADT is functorial, can we say the same about parametrized ADTs, which is kind of useful. You use these all the time. Because you may have a structure, a type that receives another type in order to be quote unquote complete. Um, so the first thing is that what he calls items that have no dependency on the type parameter, such as the nothing in maybe and new in the list case, and they are equivalent to the const functor, as we have. I think he mentioned this before as well.
Yeah.
Because the const functor ignores the type parameter, just like the const function, right? That's kind of like they are kind of related. Um, and then there are the elements that have a parameter that we need to care, such as the just in this case. And then we have the simplest, most type that cares about its parameter, which is the identity type, right? And then we can
It's very
easily
it's
go on.
very empty.
It's very empty, and we can easily implement the functor for it because this is just a tag holding some data. Well, in this specific case, a type, and we want to get the value of that type and apply a function f using fmap. Um, so then we go to a very unexpected route, which is we can define a maybe using const and identity, right? Because the const ignores the second thing that is coming, right?
Right.
Uh, and the identity preserves the only parameter that it has. So then we can easily rewrite maybe using an either with the constant identity, right? Uh, so then we already seen that the composition of functors is a functor. We can easily convince ourselves that the same is true of bifunctors. And then we want to know if the composition of a bifunctor with two functors works on morphisms, right? And then we're gonna
Right.
use this new type here as a way to reach that conclusion, right? So in here you have a bifunctor, not bifunctor. Is this the? No, it is a bifunctor BF, right? You have a functor FU and G. We have functors FU and GU, and you have the two regular types A and B, and
Um,
they are defined in this manner here.
yeah.
Then um, only BF is itself. The other are functors. We know that. This is the implementation, which leads me to believe that the author of this book used the same package to write the code that I used in my papers, which is kind of funny because this arrow here is very indicative. Very indicative. He for some reason removed the colors, which well, some people like that. But it really seems that we are using the same stuff or very close stuff in LaTeX. But that's just a parenthesis. And this is the implementation of this bifunctor, right? Which is very, very, very expected. Very expected.
Very natural.
Very natural. Um, which and this may be confusing because there's many things in here, right? There's many things in here.
Yeah,
Uh,
it's a type with 5 parameters. Let that sink in for a moment.
yeah. So again, BF is the bifunctor. Fu and Gu are functors, and A and B are regular types, right? And they are organized in this manner here. They
Very
are
lispy.
organized in this manner here.
Very,
Then
very lispy.
the implementation of that, if you want to implement a bimap, right? So here we're using this structuring to get the bicomp stuff. So this X here, this X is pretty much all of
It's this
this.
entire thing. Yeah.
Yeah, is all of that. And then we are just reconstructing constructing one of those, but applying the because we can in this particular case, right? Because we know that the FU and G or F maps are functors, sorry, so we can use F map using F1.
And
Uh,
F2 as well.
yeah, pretty much. Pretty much. Oh, okay. I was confused because there was bimap occurring after the equals, but this is because BF is a bifunctor, right? So this is overloading the things. This bimap is not the same bimap as this, right? That's important
Indeed.
to highlight. So then we have the explanations of the type tetris that you need to convince yourself that it works, it makes sense. And then we have this is the final type signature of this monstrosity here. So this is the type. Um, and then it comes a very cool thing, which is that the GHC's Haskell compiler can actually perform some stuff automatically for you. So in this case, we have the language extension derived functor, in which you can ask the compiler to mechanically generate a functor for you. I used this once before, and I even believe there is a derived applicative one. If I'm not mistaken, maybe I am mistaken. I don't. I knew the functor beforehand. I just don't know if the I may be misremembering it. Um, and then that's cool. The same thing that we can do with the equals. Then we have an entire subsection dedicated to functors in C++, which are kind of depressing because apparently there is a language limitation about templates with templates, which is kind of sad. Which is kind of sad. Yeah, this is impossible because fmap is a template parameterized not only by the type but also by the return type of the function that is being applied to it, right? Virtual functions cannot be templatized. I don't know how to pronounce that, but
Templatized.
in C++,
Turned into a template.
yeah.
I
The
would have actually written templatified because it's more hackish.
more hackish. Mm-hmm.
Hello, Fernando. We're doing book club.
Hello.
Hello. And this is being recorded, by the way. Then we take a look on the C++ code to make the same tree. So for those not initiated, this is a binary tree. that has the case of a leaf and the case of a known leaf thing.
It's a very strange tree because it cannot be empty.
It cannot be empty. It cannot be empty.
Oh,
Also,
but
all the data is at the leaves, which some trees do that. It's nice sometimes.
Yeah. Fernando,
what's
do
the
you want to ask?
subject? Yeah, what's the subject of the chapter?
Uh, we are
Functoriality.
yeah
We're
we are
looking at
looking
bifunctors and
no
other stuff.
we are looking at the family of something called functors, right? So chapter 7 was about introducing the functor to us. The what we are about to check is the covariant functor, and we're gonna see that this guy has a family. It has like a parent and a mother and a brother, and the brothers they fight, right? They are the opposite of each other.
Yeah.
Um, but
That's a very strange way to describe it, but okay.
no, it is exactly that, man. It is exactly that. And then here is the C++ well attempt to make it, because uh, this is very like a lot more work to get this done. Maybe somebody will even say that because the amount of work is this much, you shouldn't try it, which is understandable for production code, but for learning, and I think it's worth it.
It's kind of silly how big this is compared to the Haskell version.
Yeah, it's very big. But we are kind of accustomed to that, and this is also can be derived, right? And I know this for a fact because I actually did my own tree like this, and I actually asked to derive the functor like this, exactly like this, which worked as I wanted. Then we're gonna go back to the Kleisli, well,
Wisely.
Kleisli category thing again, which is the example that we were introduced with was the writer like to do logging stuff. Although, as far as I can tell, this is a very inefficient way of doing that in Haskell, but that's another conversation. And what we're gonna do, we're gonna try to see if we can make it. We can work with functors with this guy. So here's a composition operator again, right? So you have a function that takes an A, returns a writer B. Then you pick another function that takes a B and returns a writer
Returns
C.
a writer C.
And then you're gonna compose the A directly into the writer C. That's basically what we're gonna be doing. Then you can have the pure operation, which in the monad type class is called return. And basically,
It takes a
this.
pure value and just injects it into the
Mhm,
monads.
yeah. Then we can actually check it out, the fmap implementation of it, using a very tricky application of identity. It makes sense, but it would require some how can I say very long time looking at it in order to undercover this implementation. And the reason this works is explained in the chapter is because ID doesn't need to be a simple type at all. It can be because it's a for all. It's an existential type, I believe, as it is called. So that means it can be anything, which means that it can be for example a writer A to a writer A. And if that's the case, we can use the fish, which is this, and we can actually implement our own fmap function for it, which is cool. Which is cool. And then we can actually get rid of writer and use whatever Kleisli stuff that we may want to have an fmap operation. Um, and that will be a functor. That would be a functor. So the embellishment in the Kleisli category is always a functor. Although not every functor gives rise to a Kleisli category, which is
Yep.
interesting. Then we have the parametric polymorphism coming as the theorems for free, such as that if there is implementation of fmap for a given type constructor, when it preserves identity, then it must be unique. And then we're gonna this is the section that took me the most amount of time. This onwards took me the most, which is a shame because we're already 19 minutes in and we're not even close to be done with 8. But okay. Uh, So now we're going to introduce because again, what we have seen so far is called the covariant functor. We're going to meet its brother, which is the opposite of it, which is the contravariant functor. Uh, Something happened to Marinho there. I'm gonna wait. Hello?
My internet had a little hiccup.
Okay. Uh, um, we're gonna just to repetition a little bit. We're gonna meet the contravariate functor right now, and the perfect example of uh, this guy is the reader, right? Because the reader fixes the thing that is coming, but it's parametric on the thing that is going out. Um, and here's the problem. Well, not the problem. We're gonna go this further, but there is a rule of thumb that you can use to identify if your functor is a covariant and a contravariant because of that. So you can find more about this if you search covariant and contravariant FP complete. Yeah, so this rule of thumb that I'm explaining here, you can find it in this blog post here, which will explain the same thing that we are seeing it in the book, but with a more, I don't want to say mechanical, but a more like a pattern matching with your mind, that you can look at something and immediately tell if it's going to be a covariant or a contravariant thing. If I remember, I will try to put this in the video description if I remember. So then we.
I haven't read that, but I'm going to guess that the rule of thumb is if it's an argument to a function, then it's contravariant.
Mm-mm-mm. It's a little bit more simpler than that. So if the thing that you are parameterizing, I'm not gonna be able to tell exactly the wording, and maybe I'm gonna get it wrong, but it is something about the parameter that you care that is being parameterized, and it can vary from time to time. What is the position, if it's on the inputs or outputs? So in the case of the reader, we're gonna actually hard code the R, right? So this is gonna always be the same thing, but these can vary. What that means is that this is in the output position. So I would already try guess that is a contravariant immediately.
It's not, it's covariance.
Let's see.
It's right
Oh,
up
so it
there
is the
on.
opposite. So it is the opposite. It is in the input side that it is contravariant. Again, I don't remember exactly the wording in the, but the post will explain that inputs and outputs, what is being parametric, that you're not hard coding it, because we're gonna do the OPR thing, if I believe, if I remember, right?
You went,
Yes,
yeah,
yes. We're
there,
gonna fix the R, which means that we're gonna fix the
output.
output, which means that the thing that's being parametric is the input, which means that I think that that is the rule of thumb for contravariant. I think.
That's because um, basically the thing you are parameterizing is something you are expected to provide. You don't
Yeah,
have one.
yeah, yeah. So that's what I'm calling uh, fixing the R, but having the A parametric. That's what I'm calling that.
Yeah.
And it took me that helped me when I was looking at this stuff for the first time. It helped me to understand it better. Although this book also does a good job, in my opinion. Well, closing that, I'm gonna try to put the link in the description. Uh, so this is the reader, right? And as we have seen before, the implementation of an FMF for the reader is function composition, which is very handy. But let's suppose that you're doing the opposite. You are flipping things around. So instead of going from an R to an A, you're going from an A to an R. And you try to look at this type of signature long enough, you're going to convince yourself that this is not going to work. This is not going to work. And the reason is because you cannot get an R out of this guy with only these pieces. And that takes some time. That takes some time to digest.
Yeah. The problem fundamentally is that you don't have an A to feed to the op, right? That takes an A,
Mm-hmm.
which means you can't just turn it into a B because now you have a B which you can't give to the op. So you,
Yeah,
you kind of have
yeah,
to go the other way around.
yeah. So take a look on this. you have a function that requires an A, returns a B, but the other function also requires an A, returns a B. You don't have an A at any moment. You just have things that require A's, right? So that's the main reason it doesn't work. So as Marinho said, you need to go the other way around, right? Because because if you reverse this guy, if you reverse the direction of this arrow, then there is a way to get an A, which you can fit into this, right?
Yeah.
And there's a hint on what I said, because if you flip this arrow, you're gonna see that, oh wait, I want a B and return an R, but I want to remove these A's, like you want to like collapse them. That hints into composition immediately. Like immediately you think about it.
Yes, and this is actually the proper composition, the one that goes from left to right.
Yeah. Hmm.
Shots fired.
Well, I don't know if I would say proper, but
Well, it goes like the Unix pipeline and also in the same direction as English text. That's why it's proper, because it follows the natural direction that you are already reading in.
no, it isn't, because we were introduced in the first chapter of the book that you read one thing G after F or F after G. So it's already fixed, but that's okay. We're not going to go into that tangent. And then this is the categorical explanation of this process, right? What we just explained would be the intuition behind the discovery of the contravariant functor, but you can go this route, which is to say that suppose that you have a category C, which we know already that there is a dual category to it, which is going to call COP, which is the same. It has the same objects of the category C, but with the arrows reversed in direction. So then, consider a functor that goes from COP, the dual of C, to some other category D, right? Such a functor maps functions in the domain of the dual, going from A to B, lifting them to f of A to f of B in D. Makes total sense. We've seen this before many times. But because we know that there is the dual of the FOP, that if we remove the OP, that means that it is a function from B to A instead of A to B in the
The category
original
C,
in the
yeah, the
original
original
category,
category.
right? And that's how you see that what we did there. So you have a B and going to an A instead of the opposite. Then we're gonna call this guy, this other mapping G, and it's a mapping from C to D, right? And again, I need to emphasize this. F, capital F, is a mapping from the dual of C to D, and G is a guy that goes from C to D, right? That's important. Which is not a functor, right? That's important because we know this already. That's the conclusion after messing with this guy. However, this guy maps objects the same way the F does, but but when it comes to mapping morphisms, it reverses them. What that means is that it takes a morphism F B to A in C, maps it first to the opposite morphism, so flips it, and then it uses the functor F on it. So there is a two-bridge process. There's a two-step process to get there, right? You
You just
first,
say two bridge. That's weird.
yeah, I've seen two. I'm looking in my mind at two bridges. Like there's three stops in which the third one is the destination, and you're
I
doing
see.
two hops. So it takes a morphism A F going which is B to A in C, maps it to the opposite morphism from the dual of C, and then it uses functor F on it, effectively going to D on that. Which is very interesting. Oh, then we're gonna give this. So this will be the type signature of this G guy, right? This G guy. Which is called a functor with a twist. And this guy is the contravariant functor. So the functors that we have seen so far are covariant functors. And they are way more common in nature, in reality, and stuff. But there are use cases of this guy. You can. I think there are use cases examples in the link I already mentioned before, but I have another one coming, which is the link that I mentioned. So then we're gonna give this guy its own type class. So we're gonna call this the contra variant, and this it's basically an F map, but with the function that you're providing reversed. And in this particular instance, OP fixing R on it will be will have a contra map, which is the F map in the opposite universe of its existence.
Same
That
on the altar for using dots instead of the triple arrow.
wait, the triple arrow, you mean the arrow type, the arrow type class? Sorry.
That's actually just an alias for composition, except with the arguments flipped.
Oh, okay, okay. Well,
And in
well,
fact, it only needs the category type class.
mm-hmm.
It's very useful with arrows because it reads more naturally when you're writing arrow code,
Yeah,
but
yeah,
it's actually not from that type class, it's from category.
yeah. Well, we can talk about this later, though, because I already messed around with both the category type class and the arrow type class. And I find this composition way more convenient and way more natural, but we can discuss that later. Um, so then this is the perfect time to introduce flip, right? Because basically, basically, notice that we have to reverse the stuff that is coming. So if we flip normal composition, we can do that in intentional equality. We don't have to list the stuff, which is
The
very handy.
arguments, yeah.
And then it comes the big boy, the father of them all, which is the profunctor. So here's the deal. If you get the gem of contravariant, I think it is possible to understand what the profunctor does, although I don't have any experience with this guy whatsoever, although I know a
Well,
use case for it. Uh, but it is basically having a covariant functor and a contravariant functor at the same time with two different, like participating the same type.
uh, you understand bifunctors, right?
Yeah,
And you understand contravariants and also covariance functors, all of them individually, right?
yeah.
A profunctor just puts everything together. It's a bifunctor,
That's the
except
problem, though. That's the
instead of
problem.
having two functors, you have a contravariant and a functor.
Yeah, but that's the thing. My feeling, and this is just a feeling, is that I know the parts individually, but when you put them together, something happens that is greater than the sum of its parts. Especially if you look at this image right here. Especially if you look at this image right here. But again, I'm getting used to it. I read this chapter 3 times in total, so I think I'm getting there. Um, so we apply the name profunctor to a type constructor P of two arguments, which is contrafunctorial in the first argument, but it has a covariant functor in the second argument. Um, so this is basically the gem. So you have this is
That's the left
this is
one.
the
It's the one that's
contravariant.
contravariant.
This is
Yeah.
the contravariant one. And in here, what gets me confused as heck. You see that there is a B here?
Yeah.
This guy is going to an A, but this function tells the opposite of that. So because
I
looking
think
looking
I
at
think this
this
is
type signature, I'm completely fine with it. I'm completely fine. But this doesn't follow to this.
I think this is following the convention of okay, we choose the letters based on the order that each variable first appears. But actually, this yeah, I agree. This reads better if the first function is from B to A and you have a PAC to a PBD instead of what's written here.
So this gets me complete. The first time I've seen this, I was completely not understanding crap because I think, wait a moment, I have an A to a B, and I'm having a thing that is already a B. How possibly this can go to an A? That doesn't make sense. And
Or if it's a function type.
no, but here's the thing. I'm still uncomfortable. That's why I told you. I don't know if I understood this completely yet. Because looking at this explanation makes completely like a lot of sense to me. It makes a lot of sense. Although the
Uh,
same thing kind of happens, right? Because you have a B going to an A, but this is already an A, and this is going to a B. So only when I see it like this, when I see it like this, and I see B going to an A here, that I see that, wait a moment. If I have a B going to an A, I can pick the A, throw it in here, and get the R. Hence this. Total sense. Makes total sense. The issue is that in this other format here, in this format,
BR comes first, right?
yeah,
It's not obvious that this is an arrow type, well, a function type, a
yeah,
morphism.
yeah. So that just by looking at it, it feels really weird. It feels wrong.
I don't
Uh,
recall off the top of my head if the book here will say what's the profunctor of arrow. Um,
I
but
don't
bimap
remember.
on arrows is basically just
Oh, it
double
will.
composition. Oh, it does, yes. It's basically just double composition. You give a prefix and a suffix, and you stick the function in the middle
Yeah, we
of the
already
two.
in 36 minutes. I think we need to speed this up a little bit. So the profunctor is the guy that has a covariant side and a contravariant side. You have the dmap operation to do that, and you have the auxiliary functions as well to handle each part individually, just as we've seen with the bifunctor with first and second. Here's the drawing, and the main difference that you may notice that this arrow is pointing like this instead of like this, as before in the bifunctor case. So that's something to keep in mind. And then we have the implementation of the arrow profunctor, which I think is the same one, the same example that we have in the FP complete post. And it uses double composition. Like, if you're not comfortable with this, just pick a piece of paper and try to figure that out by yourself. Because again, you can make this make sense because you know the types of each one of these guys. You know the types because it's written here.
They are in the names as well as an extra reminder, I guess.
And get rid of this nonsensical, well, not nonsensical, but until you get to that point of getting the intuition, get rid of this thing, man. Just write it like this. Just write it like this.
With an actual arrow, right?
Because then the tetras will make sense, and then with time you're gonna get used to looking at like, wait, what?
Yeah.
I'm still not getting used to it, but that makes sense. So the thing that I want to talk about is this link right here. So as far as people told me, and I have, well, the person that told me is a reliable source of information. This is a Minecraft thing that has profunctor stuff in it.
That's from Mojang.
Yeah.
That's okay. Okay.
Like the reason I saved this link is because the guy said, "Man, this thing has profunctors," and I said, "Wait, what?" So I actually haven't looked into it. Um,
Optics. Yeah, profunctor optics. It's right there in the references. Amazing.
uh, uh, yeah,
Scroll down a little bit. Scroll down. There.
optics, profunctor optics, modular data accessors, generic point-free lenses. Yeah, so I think that's another thing. I think in Haskell, optics and lenses are the things that these other alternative functors they are used the most. You're not gonna find a lot of profunctors doing, I don't know, um, I don't know, man, a simple application. Like if you implement a game of life, you're never gonna see a profunctor there. That's very unlikely.
Yeah,
Uh,
this is more useful for doing like libraries than actual applications, I would guess.
yeah. Okay, then we are okay. We have a little bit like, let's see if we can cover this in 20 minutes. I have questions on this chapter as well.
Okay.
So chapter 9, chapter 9. Uh, I think that chapter 9 is a little bit, a tiny bit complicated to get in 20 minutes, but we will see. We can make an amend later. That's fine. That's 100% fine. I just need to remember everything that I read because I read all of this yesterday. So we're gonna talk a little bit. How would you describe this though? Because it talks about so many things.
Uh, the thing that actually, the thing that actually stuck in my mind when I read this was the parts where the scurrying. Yeah, this is about like how we saw the universal construction for products and co-products. This basically does a similar thing for functions, which are obviously a bit more involved. But the thing that actually sticks in my mind is this whole like functions as an exponential type.
Yeah,
Um,
part of my questions are related to that because I don't know if I got the gem of the exponential intuition. It seems kind of weird, but let's go. Let's try to go remember as we go because again, this talks about a bunch of stuff.
okay.
Um, and let's see. Let's
Yeah,
see how fast we go.
and I read this a while back, so this will be a good refresher for me as well.
So I think the first section is talking about internal home sets and external ones. Uh, so let's read here. Bool is a two-element set. That makes sense. But a function type A to B is more than that. It's a set of morphisms between objects A and B. A set of morphisms between two objects in any category is called a home set. And this is we already have this definition before. I checked.
Yeah,
It
yeah,
just so happens that in the category set, every home set is itself an object in the same category. Yes.
because it's a set.
The same is not true of other categories where home sets are external to a category. So we need to get an intuition of what does it mean to say that something is external and internal. The first question is internal and external related to what?
To the category, basically. Um, because we were looking at the category of sets, right? Home set, it's in the name, it's a set, so it's part of the category of sets. But
Yes.
categories may be about other things that are not sets, but they still have a home set, but because their objects are not sets, the home set is obviously not an object in the category, so it's external.
Yeah, you're gonna have to repeat that because that sounded a little bit convoluted to me. Could you repeat?
Sure. So in the category of sets, a home set being a set is obviously an object in the category, so we say it's internal.
Yeah, so there is an internal set within a set.
No, 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 not within a set, within the category of sets.
In the category of sets.
Yes, it's a category where the objects are sets. A home set is a set, therefore it's an object of the category. So it's internal. It's an internal home set.
Yeah.
But a category can have objects which are not sets, but it will still have a home set, which is the set of all morphisms between two given objects, right? But
Oh, okay. So I think I get it. You cannot run from it. You always will have at least one set.
yes, because a home set is literally just, okay, here are all the arrows between these two objects in a given category. So you can, I'm not gonna say trivially, but you can very easily say, okay, here's an arrow from A to B, here's another arrow from A to B. You just collect all of them and say, here's the home set from A to B in the given category.
Yeah. Yeah, no,
But
that
the
makes
thing
total
is,
sense.
yeah, but the thing is, if the objects of the categories are not sets, then the home sets obviously cannot
It's an
be inside of
intruder,
the category.
right?
It's something else. It's external to it.
Yeah, it's an intruder. Like nobody here is a set. What you're doing here, bruh? And then the answer
Yeah,
is I am external to you guys. But you cannot run from me. I need to be there.
basically.
That's cool. That's cool. Now this image makes a lot more sense, actually. Yeah. Okay, that was very helpful. I appreciate that. Uh, uh, so we have used universal constructions to define product type and co-product type. We've seen this before when talking about the initial object and the terminal object and stuff. Which is about universal construction is about defining defining objects, characterizing objects based on their relationships instead of talking about what they have within.
Yes, you're basically describing an object in terms of its morphisms,
Yeah,
how it relates to other objects.
yeah,
Which, if you think about this, kind of reminds me of abstract data types, actually. That's a bit of a tangent, though. Let's
yeah,
not.
yeah. We can talk about that later. So we need a pattern that involves three objects because again, we are now kind of trying to make a generic approach to looking at functions. Not functions,
Yes,
but morphisms. And then we need a way that involves the three things: the function type that we are constructing, the argument type, and the result type. So very naturally, the things that we're going to use is function application and or evaluation, right? Um, so
very
given a
Lisp-y.
given a candidate for a function type, let's call it z, right? So the function type is the arrow. That's very very important. Uh, the previous chapter and the reader when we were whatever chapter we've read introducing the reader, that's when you need to get used to the function type, right? Because it's very unnatural. Because from at first glance, you judge that this is just some syntax in Haskell, but it isn't. It isn't, which is kind of mind bending a little bit. But let's continue.
Amazing.
So the function type we're going to call it z. Uh, the argument type we're going to call it an a, and the application maps this pair to the result type b, right? Um, so this is the image that we should have in your mind, in our minds. We have three objects, two of them fixed. The ones representing the argument type and the result type. We also have the application, which is a mapping. How do we incorporate this mapping into our pattern? If we are allowed to look inside the objects, we could pair function f inside the realm of functions inside z with an argument x coming from a, and then we could find what happens if you pick x and apply to f in b. Is there somebody there that is the output of f having an x coming? But we're not going to be doing that because that would be cheating.
Yes.
Uh, uh, but so instead of dealing with the individual parts, we can talk about the whole product of the function type z and the argument of type a. The product z, so we're going to call this z product with a is an object, right? That's the Cartesian product. So you're basically getting all the possible combinations of all the functions with all the members of A being arguments. Uh, and we can pick as our application morphism an arrow G from that object to B, right? So we are not trying to find which one is which. We are just assuming that if you pick every single function type in Z and every single element in A using as an argument, calling it X, and you make all the possible combinations, at some point you will reach some object in the category in B, right? Um, so a product of two objects Z and A connected to another B by the morphism G. This is the image, right? So you have your
Yep.
Z, which is your basically your bucket of functions. You have A, which is the bucket of arguments, and you smash them together, and G will be the morphism that at some point of the mashing you're gonna go to B.
Yeah, Z product A is basically a Lisp pair, and G is basically eval. Well, not really. It's more like apply, but
Structure interpretation of computer programs. That's what I have to say. So the question now is, would it be able to define a function object without first defining a product? Right? Would it be possible to define a function object without first defining a product? There are categories in which there is no product, or there isn't a product for all pairs of objects. The answer is no. There is no function type if there is no product type. I don't know if I understand this. Why do we want to define a function object without defining the product first?
because then you could apply the construction of functions to non-monoidal categories.
Okay, I'm gonna have to do some homework on that. I don't think I got it. But let's continue because I think we can still proceed here. We have 10 minutes, but okay. Uh, we start with a pattern of object isomorphisms. That's our imprecise query, and it usually yields lots and lots of hits, right? In particular, in set, pretty much everything is connected to everything. We can take any object Z, form its product with A, and there's going to be a function from it to B, which is what we are looking for.
Except when B is empty, but that's kind of obvious.
Yeah. Then that's when we apply our secret weapon ranking. Why is that there? Because there may be many hits on B of all the possible combinations of Z and A. How are we going to decide which one to pick? Because we want to define which one is the best one.
The
Which
most
one?
natural.
Which one is the best one? So we're going to use a strategy called ranking. And it's
Uh,
kind of similar to the
it's what
definition
we
of
saw.
product and co-product
Yeah,
about the idea of factoring something out. Right.
yeah.
Uh, so, but we're gonna get there. So this is usually done by requiring that there be a unique mapping between candidate objects, a mapping that somehow factorizes our construction. In our case, we'll say that Z together with the morphism G from the Cartesian project to B is better than a Z prime with its own application G prime if and only if there's a unique mapping H from Z prime to Z, such the application of G prime factors out the application of G. So this is very confusing to read, and I read it really fast. What does that mean? That means that if it happens that we have more than one hit, such as in this case of Z prime when doing a Cartesian project with A, having a G prime to go to B, and the same thing kind of happens with Z, we're going to say that Z is better if Z prime can become Z given an H. And H needs to be unique.
Yep.
So it's the same kind of strategy that we've seen before with product and co-product, of having, trying to find uniqueness is the thing that we're going to use to define this is it. This is a product and this is a co-product because this is unique.
And yeah, in this case, we're actually trying to define, okay, this is it. This is a function.
Yeah. So that's basically the ranking strategy. That's basically the
I
ranking
really like
strategy.
this picture. It's very nice.
Man, the funny thing is that you would think that somebody writing about this would try to, I don't know, go to some very uh, fancy mathematical library in LaTeX and just make it, but I'm pretty sure this is hand drawn.
It looks like crayon, actually.
No, okay, then I don't know. But it looks very, very rusty, very sketchy, which is kind of good because it makes it a little bit more intuition driven rather than fanciness, right? Anyway, so here's explaining basically what I just explained. Basically what I just explained. We can define not only products of objects but also products of morphism. Since we're not touching the second component of the product, yeah. So since we're not touching the A here, going from this to this, we are just using ID, which makes
Yeah,
sense then because we're
yeah.
preserving the A.
This is basically using the what we just established about bifunctors, right?
Yeah, pretty much. So then, the third part of the universal constructor is selecting the object that is universally the best. Let's call this object, this function object, a double arrow. Is that how you call this? Double arrow, I think.
It's a very thick arrow.
Thick arrow to be. Um this object comes with its own application, right? A morphism from that Cartesian project with A to B, which we're gonna call it just cause eval.
This is the best picture so far because it has eval in it.
The object, this very special object, is the best if any other candidate for a function object can be uniquely mapped to it in a way that its application morphism G factorizes through eval. This object is better than any other object according to our ranking. So basically, what we are defining formally, a function object from A to B is this object right here with this notation together with this morphism here. which is,
Eval.
yeah, such that for any other object z with this morphism, there is a unique h that factors out the g using eval.
Amazing.
So basically, every single morphism that how can I say this? Every single g prime that attempts to do this is worse than eval because eval can factor that out, basically.
With the help of age, yes.
Yeah.
A
Of
unique
course,
age, to be more precise.
yeah,
Yeah.
unique H. There is no guarantee that such an object exists for any pair of objects in a given category, but it always does in set. Moreover, in set, this object is isomorphic to the home set. I actually don't know if I understood this. Why this is always the case in set? For
Ah,
as such an object exists for any pair of objects in a given category, but this is always the case in set. Hmm. Why?
I think it goes back to the what I mentioned earlier about sets being unusually connected. Like pretty much everything connects to everything else.
Ah, okay.
I'm not sure exactly about the exact details from that guarantee this result. But it seems like a logical consequence somehow.
Yeah, we probably should go back and try to understand that a little bit better because I think in this book these type of holes, if you don't patch them, it's not gonna go well.
Yeah, it's been a while since I read this. I actually kind of forgot some stuff, so
Yeah, which is expected. Again, I apologize because it was my fault.
it happens.
Then it's gonna come something very unusual, explaining curring using this thing, which is a very, very, very debatable way of explaining that to newcomers. Very debatable. But that's okay. Reading the book. If you're already reading the book, maybe the author is just assuming you're gonna get it. Come on. Uh,
He has faith in the reader's abilities.
so we're gonna look again at G. G is going from the Cartesian project to B. So being a morphism from a product comes as close as it gets to being a function of two variables, which is makes sense, right? Makes total sense. In particular, in set, G is a function from pairs of values, one from Z and one from A. Again, expected. On the other hand, the universal property tells us that for each such G, there is a unique morphism H that maps Z to a function object A to B. That's not. Oh, that is how we do it. In fact, that is how we do it. Okay. Yeah, that is always the case. In set, this just means that H is a function that takes one variable of the type Z and returns a function from A to B.
Yeah, the double arrow is missing from that type signature.
Do you mean this one?
Yeah, there
I
should be
think.
an arrow between A and B. That seems like a bug in the PDF.
Oh, okay. That makes way more sense because I was kind of trying to understand what is the spacing syntax. Makes sense that it seems to be a bug. That makes H a high order function, and the reason is because H is a function that takes one variable from Z. Z is a
Returns a
set.
function.
Z is a set of function types, right?
Yeah, it's a function type.
And returns a function from A to B. So we are going from functions to functions. Is that it?
Yeah.
Okay. It is in fact a higher order function then. Therefore, the universal construction establishes a one-to-one correspondence between functions of two variables and functions of one variable returning functions. Makes complete sense again. I think we first seen this in when doing the interpretation of the monoid, I believe.
Yes, it was.
This correspondence is called currying, and it is called the curried version of G. So again, this is 100% not wrong. This is 100% not wrong at all. It's just because after you dump all of this uh, set of epiphanies into the reader, I think it's a little bit unfair to just say, okay, so here's the thing.
I mean, I mean, currying is a natural direct consequence of what we just saw, so logically it makes sense to place it here, but
Come on, man.
yeah, the pacing could be better, I agree.
Like this could be in chapter 1, man. Like there is no way around it. If you change the notation and change the explanations, you can 100% explain curving without using this. Although I need to be fair to it, which is to say that this is not really that complicated at all, because we know that this is a function, right? We know this is this is a set of functions. We know that this is a set of arguments. So it kind of makes sense that this is the uncurried version of this. Kind of makes sense, but again,
Um,
again,
not, not quite. It's more that like um, okay, so you have the z, right? And then you have the age. Age returns a function. It's like you just saw age being used in the construction of functions. There's a deep relationship that's being hinted at here.
no, it is especially this one. I think this is one that portrays the best. Here you have a thing that gets a Cartesian product and returns a b. It just so happens that this thing is a function.
Yes.
So you can write it like that. You can do it in this way. I'm not saying you can't. I'm just saying that this is very deep stuff to get your mind around, to grasp. Um, um, so yeah, so I think but that's basically
Actually,
current for you.
if you scroll down just a little bit, yeah, the formulas for currying and uncurrying.
Oh, they are definitely
Actually,
here. They are definitely here.
no, this correspondence is one to one because given any g, there's a unique age, and given any age, you can always recreate the two argument function g using this formula, and there it is.
Yes, this is the trick, right? Uh, and again, this is very deep stuff. I don't even know if I got it completely, but the intuition is in my mind, which is kind of what this book is trying to do. So currying is essentially built into Haskell syntax, which is facts, right?
True.
So we can
Yeah.
read this as this. I think actually this comes even before. I think this is a lambda calculus thing, if I remember correctly. At least the
Ah,
first time that I seen currying at all was when we studied lambda calculus.
I mean, if you're trying to minimize the number of rules that you are using to define your calculus, then yeah, currying is the way to do multiple arguments because it's like less. You need less infrastructure. You don't need to have pairs as a built-in part of your syntax.
And another thing, if you have currying, that's a sign, an evidence, a piece of evidence that your programming language has functions as first class. If you have currying.
I mean, you need to be able to return functions to have currying at all. So
Yeah. So that's what I mean. Then we have some examples, right? We have some examples. So the interpretation of the multi-argument function it may look like this, but you can return a new lambda. You may return instead of doing like receive this thing. I can just return a new function, return a function that has this type. Why not? I can.
all the same in Haskell.
Yeah. So these functions are equivalent, right? So here we have strictly speaking, a function of two variables is taking a pair. You have auxiliary functions in Haskell to do currying and uncurrying procedures. So if you have a function that receives a product and you want to make that curried, you use curry. And you also have the opposite operation. You also
Yep.
have the opposite operation. And then there is there is this thing, which has a lot of parentheses, man. It has a lot of freaking parentheses.
It's fine. It's fine. Says the Lisper.
So and then there's an explanation here that there is a there is a
Actually,
way.
what bothers me about those parentheses is not the number of them, it's that they actually mean different things.
No, I that also bothers me. That also. But like you could contract these things. There's but I think that the reason that they he did it this way is to make it explicit that you have like maybe he wanted to tell
Yeah,
you you can have lambdas within lambdas within lambdas like forever.
forever
Uh,
and ever, all the time.
so here we have apparently some std bind stuff function using the template in C++. Here's a function that we did before. So here's how you do the currying. Here's how you partial apply it, so to speak.
So to
Which
speak.
I believe I haven't tested this out actually, but I believe this is the position that you are partial applying. That would make sense to me. But then it means one of two things. We're gonna put the hello on the second, or this is starting from one.
Mm,
I don't know C++ at all, so maybe this is 100% not the case, and this is just some
yeah,
necessary noise that you need to do for some random reason.
yeah, I don't know C++, like, at least not this whole placeholder thing. I know the C subset fairly well because it's C, but yeah, C++ is not really my thing.
So we have the Scala version, which is way more. Yeah, it's saying that it's more function than C++. I haven't used function Scala yet, so I don't know, but I trust that it may be because Scala is usually classified as like in the spectrum of functional languages. Scala isn't there, although not very high in the ranking. Um,
Yeah. It tries to make it easy to use Java stuff, so it's kind
sure.
of it kind of gets you stuck in this position, yeah, where yeah, there's mutable stuff happening. You
Yeah,
can't really get away from it without making it harder to use Java.
yeah. So exponentials. In mathematical literature, the function object, or the internal home object between two objects A and B, is often called the exponential. So the first question that I have is which function object are we talking about?
The categorical function object, I guess, or the arrow itself.
Oh, it's called the exponential. Notice that the argument type is in the exponent. What does that mean, man? What does it mean to say that the argument type is in the exponent?
Okay, so like if a type has three members in it, and a function takes that type and it returns another type that has five members, like let's just assume they are enums, just for the sake of simplicity, okay?
Sure.
It takes three possible values and it can return up to five possible values for each input. So that means that the number of possible functions that you can construct is like 5 times 5 times 5. It's 5 to the third power. Where,
Wait,
3 is.
I think I got 75% there. So could you repeat the beginning? You have a function that receives three things? Is
It has a
that?
function. It's a function that receives a type with three members, okay? So it's an
Yeah?
enum with just three values in it.
Yeah.
That means there are three possible inputs to the function, which means there are three different ways to call it, okay?
Yes, also yes.
For each possible way to call it, what's the output type? Well, it's B, which we in this example has five possible elements, okay?
Oh, so it's 555.
Yes, it's 5 to the third power, you see?
Oh. He should have written it like that. Because now that I have your example, I get it. But
Yeah, that A should have been a superscript, actually. B superscript A.
oh. Is that correct in your version?
I think it is actually. Let me double check.
Because
Uh,
then that would make way more sense. Way
exponentials.
more
Yes,
sense.
it is correct in my version, actually.
Okay, so I need to stop using this one and reading the one that you're using.
I can
Uh,
send you a link later. It's from GitHub.
yeah. Uh, oh, that's probably the reason I didn't want it in the beginning because I want to read it in like the fancy PDF. But
No,
okay.
but it is a PDF as well. It's
No.
just, you
Okay, so
know,
then I'm just stupid. This notation might seem strange at first, but it makes sense if you think of the relationship between functions and products. Now all the other things down here, now they will completely make sense. Ah, I'm so fucking stupid. But okay. This notation might seem strange at first, but it makes sense if you think of it. We are already seen that we have the to use the product in the universal construction of the internal home set, but the connection goes deeper. Um, so then we go to some examples of memorization, because blah blah blah. Because if you have a non-infinite amount of, oh, I'm gonna say if you have reasonable amount of stuff in your sets, you can memorize them. Why not, right? Instead of doing a 1 plus 1, if you have only
yeah,
256 to
yeah.
the,
And now suddenly, if you memorize all your functions, they are just tables of data.
they are just tables. I think you were the one that mentioned this to me, right? That maps are actually they have a functional aspect to it in the sense that they actually are providing you for the same input the same output every time.
Yeah,
And this is
yeah. You
especially the
can,
case if you're memorizing it.
yeah, you can interpret a dictionary as a function
Yeah,
in that way.
yeah. So for instance, a pure function bool is completely specified by a pair of values. One corresponding to false and another one corresponding to true. The set of all possible functions for bool to say int is the set of all pairs of ints. Of all
Because
pairs of ints.
pairs, because bool has two values. You see.
Oh, so we are just doing a Cartesian product with a bunch of falses and a bunch of trues and all possible ints.
Yeah, basically a function says, okay, for false I return this and for true I return that. So a function is basically a pair because bool has two values. And the pairs are from ints, which means you have a bunch of possible, depends on
Mm-hmm.
the size of the int, right, to
Mm-hmm.
choose from.
Mm-hmm. It's kind of funny because yesterday I stopped reading at the same sentence because I didn't understand it, and then I understood and moved forward, and today I forgot about it, and now I get it again. Uh, the other example is the 256 values. Haskell uses Unicode. That's true. There are several functions in the library that these lookups. So a tuple is a product type. So we're dealing with function products of 256 booleans. 256 booleans. We know from arithmetics that an iterated product defines a power. If you multiply bool by itself to 256 times, you get bool to the power of that. Basically, right? Makes total sense. This is not supposed to be a surprise. So how many values are there in a type defined as 256 tuples of bool? Exactly 2 to the power of 256 in the type defined as 256 tuples of bool. Yes, 2 to that power. This is also the number of different functions from char to bool, each function corresponding to a unique 256 tuple.
Yes,
The
because it
number
just
of
says,
different
okay,
functions
for
from
each
char to
possible,
bool.
yeah, a function from char to bool, you can think of it as a lookup table, right?
Yeah.
For this char, I return this boolean, and you do that for every possible char.
Yeah, but why 2 to the power of that?
Because a char is 256.
Yes.
Oh, it's 8 bits, so it's 200. There are 256 possible chars. That's
Yes,
the number of
that's still
elements.
correct. Uh, the number of functions. The number of, so the number, oh, the 2 comes because there are only 2 booleans.
Yes, that's your output type.
And the 256 comes because we have 256 characters.
Yes.
Uh, so the thing goes as follows. The output defines the base and
Yes.
and
The input is the exponent.
which we've seen before. We've seen this
Yeah, it's
before.
where yeah, it's where I said yeah that BA should be a B superscript A instead. And in
Yeah.
my PDF it actually is.
You can similarly calculate the number of functions from bool to char And the reason that is because the outputs is from bool
Yeah,
to
you can
char.
choose. Yeah, you can choose up to 256 different outputs, and you have to do it twice because you can either receive true or false, and you have to define your output for both possible inputs.
Yeah, but here's the thing. Here's the thing. Oh no, that makes sense. It is 100%. It is symmetrical with the other one. The exploitation for function types makes perfect sense in these cases. Yeah, so this is 100% in the context of memorization. That's what I got it wrong. Okay. So there is
You
stuff that
probably,
you cannot memorize easily, which makes sense.
you probably wouldn't want to fully memorize a function from int or double. Well, yes, because those types are like pretty large in terms of number of possible values.
Eager memorization of functions from these types. Well, in a Turing machine, the classical definition of it, they are actually infinite because the tape is also infinite. So, but Haskell is a lazy language, so the boundary between lazily evaluated data structures and functions is fuzzy, which makes sense because in Haskell you can have infinite stuff because of all that laziness.
Yeah, as
Uh,
long as you don't look at it all at the same time, right?
or you don't have
It's
to
the
calculate the
whole,
length.
yeah. Well, to calculate the length, you have to look at it all at the same time. Well, not at the same time in the sense of holding onto the memory, but you have to reach the end and there's no
Mm,
end, so you're stuck.
yeah. Uh, so there is a larger family of categories that can be used to that purpose. The category of sets as the model of types and functions. These categories are called Cartesian closed. A Cartesian closed category must contain the terminal object, a product of any pair of objects,
And an
and
exponential.
exponential for any pair of objects.
So basically, you need to be able to, you need to have units, you need to have tuples, pairs, and you need to have functions. That's, to put it in concrete terms, right?
Man, okay, this is a separate thing. We're gonna have to talk about this offline later. But this is reminding me so freaking much about logic programming. We're gonna talk about this later, but this the same conditions even, but different terminology.
It's
Fuck.
an
Okay.
isomorphism, maybe.
Yeah, we're gonna talk about that later. It's kind of crazy. It's kind of insane if that's the case. If I am not tripping, maybe I am. We can talk about that later. So the terminal object can be thought of as a product of zero objects. So what did you say again? We need unit because unit is the terminal object in which sense again?
It's a terminal object because there's an arrow, a unique arrow coming into it from all possible input types.
No, yeah, but you specifically said unit. Oh, it's because unit the function, right? You receive anything and
Uh,
just return the things.
yeah,
I see. So what's interesting about the Cartesian closed categories from a perspective of computer science is that they provide models for the simply typed lambda calculus. We implemented this already, which was fun, but that's a separate thing. The terminal object and the product have their duals, the initial object and the coproduct. A Cartesian closed category also supports those two, and in which product can be distributed over coproduct.
it's called a bicartesian closed category
Bicartesian.
because it basically has rationals as types. Well, not rationals, it has, oh, technically it just has integers, right? Because it has addition and multiplication.
Yeah. I don't know if I understood why having the initial object and the coproduct leads to have to be able to be doing this. Oh, you have all of them.
It's isomorphisms, basically.
No, but you
You
have all of
can,
them.
yeah.
Okay, so in the case of having all of them, this makes sense.
Yeah, and the equal sign is not really an equality, it's actually an isomorphism.
Yes. Yeah, but yeah, that's always pretty much that's always the case. The interpretation of function types as exponentials fits very well with the scheme of algebraic data types. It turns out that all the basic identities from high school algebra relating
0 and
numbers, zeros
1,
and ones,
sums and
sums, products,
products.
and exponentials hold pretty well, pretty much unchanged in a bicartesian, respectively. Initially and final objects, coproducts, products, and exponentials. Um, yeah, we don't have the tools to prove them, which is kind of unfortunate, but we can have some intuitions about them. So this is a function. This is a function
It takes
that
void and
that
returns
takes
anything.
nothing and returns anything, and this is equal to one.
Because there's only one, the absurd function.
Ah, I think I get it. I think I'm starting to get it. I think. Okay, now, oh man, that was so. Uh, that was so mind blowing. Now that all because of the notation, all because this was wrong.
Yeah.
I should stop being stupid and just use the correct one. Okay, so that's it actually. So if you have a function that takes nothing and returns whatever, there is only one, which is the absurd function. Which
Which you
is
cannot actually implement, yes.
you can implement. You can. You cannot call it. That's a different thing.
Well,
Uh,
yeah, I suppose yeah, that's true. I
yes, it's
misspoke.
exactly this comment here. Uh, the claim
Is
is that a set of functions from void to any type is equivalent to the unit type, which is a singleton, where it means that there is only one. I see.
yes.
Every type contains the result of a never-ending calculation, blah blah blah. The second reason is that implementation is equivalent because no matter what, we can do whatever with it because nobody can use them. Well, not use them. I
Amazing.
get nobody can call it. Nobody can call it.
And if you manage to pass it a never-ending calculation, it will never return. uh,
Cool. Let's go to the other one. Powers of one.
Powers of
So if you
one
have a function that takes whatever and
and
returns only
returns
one
units.
thing, this is the unit function.
Yes.
Awesome. Awesome. So this is grabbing whatever, going like, what's the name?
It's the unit type.
No, but there is a name for this movement of doing the funneling. We've seen this before.
Oh, right. It's
Fuck. I don't remember,
yeah,
man.
it's earlier in the book. It's I want to say it's a surjection, but I'm not sure that's the right jection.
Man, but there is nomenclature for this. We are just not getting it. First power.
It's a collapsing function. Let's
Yeah,
use
yeah,
the
yeah. So if you have a function that takes a single
unit.
thing and returns whatever,
There are as many such functions as there are things in A, because there's one possible input, it has one possible output, so the number of functions of that type is just the number of elements in the type of the output. Very
that's weird.
straightforward.
That's not as straightforward as the other ones. Not at all. That's weird.
Well, basically, if you have an output type, let's say Boolean, which is,
No,
there's
no, no,
just
no. I'm
two
not
possible.
saying like I get it, but I don't know the implications of that. Yeah, it makes total sense. This explanation used to pick elements of the object A. The set of such morphisms is isomorphic to the object itself, which is what you said,
Yes,
because you said whatever many you have in one is the amount of these functions you're gonna have.
yes. And there's
Hmm.
one function for each element, so there's a one-to-one mapping. That's why it's
Yeah.
isomorphic.
So here's the deal: if you have a function that takes B or C, B or C,
That's the
and
same as a pair of functions, one taking B and another taking C, and both returning A, and you just select which one depending on the input type.
but this is a
Oh, depending
Cartesian
on the input
product.
tag, actually.
Wait, I
A
think I got
yes,
lost. What is the Cartesian product doing there?
a pair. Basically, a function that takes an either is the same as a pair of functions for each branch of the either.
Which makes sense. It should be that.
Yes,
But I still
yes.
don't see why your explanation is not mapping to this symbol to me.
Because that's the product. It's literally a pair.
Ah, okay. I was imagining it wrong then. It's not like a total thing. It's like pairs.
I mean, it is a total thing because how many possible pairs can you build out of the, well, A and B on the left and right side of the pair? It's just however many A's there are times however many B's there are. So that's
Hmm.
why it's using the X multiplication symbol for the pair.
I see. A function from a sum of the two types is equivalent to a pair of functions from the individual types. This is just the case analysis that we use when defining functions on sums. Instead of writing one function definition with a case statement, you usually split it into two. Definitions with a case. Yeah, that's exactly what you said. That's exactly what you said. So now here's the thing. What is this
Higher
supposed
order
to mean?
functions.
Yeah,
It's a higher.
because this is a function that takes a b and returns an a, but
No, it's
then
a function that takes a C and it returns another function that
that
takes a
takes a
B and
b.
returns an A.
That's correct. And the outcome of that is an a b with c.
That's basically currying, essentially.
That's basically currying.
Yes,
Actually,
because
no, this is the curried version then.
yes, and the uncurried is on the right.
Ah,
See, it takes
that's kind
a
of
product which is
insane.
a pair.
That's kind of insane, man. It's even more impressive than the math on chapter 3 or 4 or whatever. Huh. I guess there is a reason to call them algebraic then. I guess there is a reason. Okay.
And
Uh.
now you're probably curious about that paper, that obscure paper I shared about rational types with negatives and fractionals.
Oh yeah. What are those supposed to mean? Insane, insane. Let's move on. So now if you have a Cartesian product, so this is a function that takes a c.
And returns A and B
Wait a
as a
moment
pair.
before you explain. Before you explain, this is this is saying that a function that takes c and returns a pair has the same amount of stuff as the two things separately combined.
Yes, because how could you implement such a function? This is just more of intuition. Um, you have a pair of functions, one for each element, and then you just pass them the same inputs, and there's your pair.
No, you call the function for each one of them, right?
Yes, you have an input C, you have your pair of functions, you pass C to both of them, and there's your pair.
No fuck. Okay, we are way over time, but let's try to do this in 3 minutes.
Harry Howard, the famous one.
Yeah, so the equivalence between, oh man, I always forget. Every type can be
It's big.
interpreted as a proposition, a statement or a judgment that may be true or false. Such a proposition is considered true if the type is inhabited. Oh, so if you have a logical proposition and this ends with true, that means that there's somebody in there.
Yeah, the type is not empty, it's not void.
Yeah, yeah, I remember now. An implementation of a function is a proof. Writing programs is equivalent to proving. Let's take a function eval we have introduced in the definition of the function object. Its signature is. So we have this thing. We have this thing. It takes a pair consisting of a function and its argument and produces a result of the appropriate type. It's the Haskell implementation of the morphism this.
The one we defined in chapter 8.
I see.
Oh, not chapter 8, it was earlier in this chapter, I think.
Yeah, that's why I said these two chapters are insane. Just insane. Which
It's
defines a function
madness.
type this. Let's translate this signature to a logical predicate using the curly hardware isomorphism. So what did we do there? What have we done? So
Basically, pairs is and functions are logical implication. So we are basically saying if you have an A and you have a proof that A implies B, then, well, you just implied B.
This makes perfect intuitive sense and has known since. If it's true that B follows from A and we have an A, yeah, modus ponens,
Yep.
100%. We can implement it, which is cool. Uh, uh, if you give me a pair, blah blah blah. By implementing this function, I have just shown that the type is there is somebody in there.
Yes. There is, in fact, a value of that type. And the value is the proof that the type as a proposition is true.
But which value is that? Can we discover that?
It's the implementation of eval just above, like under the type signature. The implementation is like,
Oh, this is the guy. So this
yeah,
is not only showing that it is inhabit, but it's showing who is in there.
yes.
This is obviously false, right? This is obviously false because there may be a right on that. There may be a right on there, and then you are screwed. Then you are completely screwed. The absurd function is basically absurd. It's basically I don't really know in Portuguese this though, which is that from nonsense everything follows, anything follows.
Yeah, it's right there in Latin even. Ex falso quod libet. I'm not sure if I pronounced that right because I don't know Latin, but you know.
Uh, Here's one possible proof of this statement in Haskell. Uh, the type void is strict. This definition makes it impossible to construct a value because in order to construct one, you would need to provide one. Therefore, this new type is confusing me. This makes total sense that you're not going to be able to call it, but this is kind of weird.
You're basically saying in order to construct a void, you need to have a void, which is obviously impossible, right?
Yes. And it's basically doing some marketing for Agda and Koch about languages that you can actually leverage this type of stuff more consistently in some real world problems. Because although you can
Yeah.
do this stuff in Haskell, well, this is a very hot topic. I'm gonna try to dodge that, but these languages are more proper to use this type of this Curry. What's the name again? Curry Howard isomorphism.
Yeah, and there are other options like Idris and Lean and
Maybe
other
Isabelle
that
as well.
yeah, dependently typed languages in general.
Yeah.
They are
And that's the end.
typically
So we did it in 1 hour and a half.
a
one
bit
hour and
longer
a
than
half.
usual, but I think that's fair given the long break. So,
So goodbye.
bye, future people.